Let's understand the same behavior by looking at the linearized transformation near the fixed points of the system. So here are our equations of motion, and then we can look at the Jacobian matrix, the matrix of the derivatives of the transformation. The first term is take the right-hand side d by dA, so that's 1 minus 2a plus epsilon b. And then I take d by dB of the right-hand side of the a dot term, and that's plus epsilon a. And then I have epsilon b, 1 minus 2b plus epsilon a. So the fixed points of the system are, first of all, 0, 0. That's an obvious fixed point of the system. And here the Jacobian matrix is 1, 0, 0, 1. Lambda plus minus are both equal to 1. It's doubly degenerate. And this is an unstable fixed point under all conditions. Then there are the single species coexistence points 1, 0, or 0, 1. Let's just look at 1, 0. Let's not worry about 0, 1. And here the Jacobian matrix is minus 1, epsilon, 0, 1 plus epsilon. And for this matrix, the eigenvalues lambda plus minus are equal to minus 1, 1 plus epsilon. So the behavior of this fixed point depends on the value of epsilon. It's a stable fixed point if epsilon is less than minus 1, because then both eigenvalues are negative. And it's a saddle otherwise. And so 0, 1, there's similar behavior. And finally, the coexistence fixed point is given by 1, 1 minus epsilon, 1, 1 minus epsilon. And all of these fixed points are easily determined just by setting a dot and b dot equal to 0. So I'm not bothering with that. I'm just enumerating the fixed points. And in this case, the Jacobian matrix is given by minus 1 minus epsilon, epsilon divided by 1 minus epsilon, epsilon divided by 1 minus epsilon, minus 1, 1 minus epsilon. For this matrix, lambda plus minus is equal to minus 1 and 1 plus epsilon divided by epsilon minus 1. And so this fixed point is stable if the absolute value of epsilon is less than 1. And notice that when epsilon is bigger than 1, this fixed point doesn't exist because it's off in negative space.